Hello, everyone. Hope you're doing well. Thanks for all the love and support from you guys on my channel, and I hope you are enjoying mathematics in a better way. It's been a very long time. I have not uploaded any video on my channel. Today, I am back with a mini introductory lecture to one of the most fundamental concepts of mathematics, that is derivative. Yes, you heard that right. Derivative is essential to learn calculus, which has many applications, including engineering, business, finance, industry, economics, physics, and whatnot. Today, I will be adopting the same strategy which I usually use in other video lectures. It's WWH, what, why, and how. Because I told you, if you are trying to get any new concept, so you try to actually find an answer to these three questions: what is it, why is it, and how to do it. So let's see how to adopt this to understand derivative. Without a further delay, let's get started. Let's get started. Introduction to the derivative. So this is how we will proceed towards understanding the meaning of derivative. Firstly, we'll have some motivation to study derivative. This will answer why we need to study it or why we need to understand it. Then we'll understand a real-world example, and using that example, I will build upon an intuitive way of understanding the meaning of the word derivative, followed by geometrical understanding. The reason I have included this geometrical understanding here is simple. I believe that whenever you are trying to understand anything, so it's best you visualize it graphically or geometrically, because that way you tend to retain it for a longer period of time and the clarity is more. This is the reason for including geometrical understanding, followed by the mathematical definition, which is really important to understand. And this whole together will form the answer to the what part, what is derivative. And last but not the least, I will be giving you a computation example showing you how to compute the derivative of a given function using the mathematical definition. So the last part is actually going to answer the question, how? Let's begin. So whenever someone asks you why you want to do a particular thing, what you try to give reason as a reason is you explain the benefits, that I want to do this particular thing because this has so many benefits or applications, or I love doing this, or something like that. So most of the times we are trying to building up reasons for doing anything in terms of telling their uses or applications. So in the beginning, I told you derivative is nothing but a fundamental concept in mathematics, and it is a foundation stone of calculus. Calculus is a study, it's a basic area of mathematics which has got so many applications in engineering, physics, computing, finance, business, economics, and whatnot. That's the reason, that's the motivation behind studying derivative. Now let's move towards the real world example. I could not think of a better example than COVID-19. I believe most of the people on the world have been directly or indirectly have been affected by COVID-19 in some or other way. So there is no one, I suppose, who is not aware of COVID-19, the global pandemic. So let's see how I'm going to use this example to build towards the understanding of the derivative. Most of the mathematicians around the world are actually trying to build a mathematical model with an aim to understand the dynamics of the virus. Now, the term I have introduced here is mathematical model. This whole is a totally new concept. So if you want to understand about mathematical modeling in detail, so there is a separate lecture for that. But right now, I would just say mathematical model is something which is kind of a formula or a pattern which tries to give an answer towards a real world problems. So mathematicians are trying to understand the dynamics of the virus. Obviously, the aim of understanding the dynamics is clear to everybody. We want to get rid of that disease as soon as possible. So through mathematical modeling, one can do that. Another important word here is dynamics. Dynamic means something which is changing, which is exact opposite of static. Static means something which is not changing. It does not change. It's just fixed at its position with respect to space and time in general. So if we are talking about anything is dynamic, that means it is changing. It is changing with space or it is changing with time. So let's have a look at some data. So this data has been collected from the website of Worldometers. So let's talk about number of newly infected cases in India in 2022. April 15, the number of newly infected cases in India were 975. In April 16, 1150. April 17, 2183. So I have presented here three different numbers for the number of infected cases in India on three different dates. So can you see the trend? So if you are a mathematician, or even if you are not a mathematician, just have a basic understanding of the numbers, you can answer this question that the trend is actually increasing. The 975 goes to 1150 on the next day, 1155 increases further to 2183 on the next day. So the trend is going towards increasing. So this is the information we are deducing from this much data, that the number of infected cases is actually changing. Now, any number can have two types of changes. Either it can decrease or it can increase with respect to time. So this data tells us that the number is increasing. Now, why I am emphasizing on this, it will be clear in a moment. Let's have further look at number of new infected cases in Canada. So here also I have taken three different dates of 2022, April 12, 11090, April 13, 13,969, April 14, 19,215. So here also, if you look at, the trend is increasing. That means the number of newly infected cases is increasing with respect to time. So the information deduced from the data is qualitative. What does that mean? That both sides, I am saying that here also the number is increasing day by day, and in Canada also the number increasing day by day. So increasing is just a qualitative information. It does not give us much details about what exactly is happening. Does that mean that situation is equally worse or equally severe in India or Canada? So we cannot get that if we just know that the number is increasing. A much better question would be, at what rate it is increasing? So most of the times we are not interested in something is changing. We are interested in how much it is changing. So actually we need to do the quantification of the data. So let's do the quantification of this information. So that means we will be giving our answers in terms of numbers rather than just saying increasing. So let's compute the rate of increase for both the cases. So rate of change for India is 175 cases per day. So I have considered these two. So the difference between them is 175. So if I say per unit time, that means per day, how many new cases are appearing? So they are 175. And the rate of change for Canada, on the other hand, is 2879 cases per day. So what I've done is try to give a better picture of the actual situation. So instead of just looking at the numbers, what we are actually interested in, the computing their rate of change. So you can see the rate of change of anything which is measurable gives us a better understanding of its scenario or situation. So these numbers are more important than these numbers, because earlier we just had the information both of the trends are increasing, but by computing rate of change we have a better understanding that the rate of change is actually higher for Canada than India. as per this data. I'm not making a general statement. It's just about these given data to me. According to that, the rate of change is higher for Canada. So here comes the intuitive definition of the derivative. So let's see how I connect that with the just studied example. So as I told you, the rate of change is an important word here. So that is the whole theme. What is the rate of change? This is nothing but a derivative. So derivative, if somebody asks you what is a derivative? Derivative is nothing but rate of change of one variable with respect to another. One variable with respect to another. So there are actually two variables involved. One of the variable is the dependent variable and the another variable is independent variable. So in previous example of COVID-19, dependent variable is the number of COVID-19 cases and the independent variable is time. In real world, most of the things are dynamic. That means there is something which is always undergoing change. So that change can be with respect to space and that change can be with respect to time. So the space and time are usually the independent variables because they are changing by themselves. While the other quantity which we are measuring, the unknown quantity, that is the dependent variable. So whenever we are trying to understand derivative, the fundamental concept is there is involvement of two variables. One of them is dependent and another one is independent. The change is happening. So the rate of change is nothing but the derivative. I hope this intuitive definition of the derivative is clear. Now let's have a look at the geometrical understanding of the derivative. So here I have the graph of a randomly drawn function y is equal to fx. And on the curve, there are 2 points marked, point A and point B. The coordinates of point A are x0, fx0, and the coordinates of point B are x0 plus h, fx0 plus h. So this much is the h. So we have changed the independent variable. So this side we have x, this side we have y. So our x is the independent variable and our y is the dependent variable. So I have changed the independent variable by an amount that is called an increment, and that increment is h. So upon changing x from x0 plus h, the change in the function is fx0 to fx0 plus h. So what I'm doing is measuring the change in the dependent variable, the unknown variable. So that change is this, fx0 plus h minus fx0. And the change in independent variable is h, because that is x0 plus h minus x0. So this is h. So if you divide these both quantities, you get a ratio, and that ratio is nothing but slope of the line AB. So I hope through basic understanding of mathematics, everybody is able to understand this one, that how this quantity is the slope of this line segment AB. You can call it secant AB or the chord joining AB, whatever you want to call it. So this quantity, the change in dependent variable divided by the change in independent variable, nothing but the slope of AB. So let's see what to do next. Now I further reduce the value of h. I am bringing the point C closer to A. Earlier it was AB, but now it is AC. I have in magnitude decreased the value of h. I'm still calling it h. You can call it h dash or something, but I'm still using the same variable h. So this time, the slope of the line segment AC is given by this quantity fx0 plus h minus fx0 by h. So the line segment AB is now reduced to AC. So let's keep on doing this. Further reduce the value of h, and now I have the slope of the line segment AD. So you are actually becoming closer and closer to the point A. So that means this h, you started from this much h, then you had this much, then you had this much. So h is decreasing. So you keep on doing this. So h should become smaller and smaller. So in other words, h approaching to 0. And what is happening on the y side? The secant is becoming the tangent at the point A, because essentially what is going to happen here is when you bring this point closer and closer to A, all these secants are eventually going to convert to a tangent at the point A. So the slopes of all these secants are going to approach the slope of the tangent at point A. And that slope of the tangent at point A is nothing but the derivative, because then we know the rate of change of the function with respect to x at a particular point A. Because when I say derivative is the rate of change of one variable with respect to another variable, it's an incomplete statement. I should be more precise in telling at what point the rate of change it is. So the derivative should be mentioned point wise. Derivative at point A is nothing but the slope of the tangent at A. So this way, what I'm actually noting down is instantaneous rate of change of fx at the point A. So derivative is not just the rate of change, it is actually the instantaneous rate of change at a particular point. So similarly, derivative of the function at some other point, say B or D or whatever, will be different because the function is varying in a different way at different points, right? So I hope the geometrically it's clear about what is the meaning of the derivative. So to summarize this, I would say geometrically derivative represents the slope of the tangent at that point, provided the tangent exists, right? And now we move forward towards the mathematical definition. So the derivative of a function y is equal to fx at a point x is equal to x naught is given by. So now it will be very easy for you to understand this definition, which we call the first principle definition, or we call the mathematical definition. If I would have started my presentation directly with this definition, I don't know whether you have understood it better, but I have tried to give you reaching towards this definition from the geometrical understanding, because now I have shown you the meaning of this h becoming 0, that why this limit h becoming 0 is included in the definition of the derivative, because this quantity by this quantity is okay, it's the change divided by the change in dependent variable divided by the change in independent variable. So, but this is significant. You cannot just compute change with the arbitrary value of h. That change should be computed at a very, very small value of h. So that's why this limit h tending to 0 is included in front of it. So this is the derivative of a function at a particular point x is equal to x naught. And what is the notation of it? So this is denoted by dy by dx. It's a standard notation, and also denoted by f dash x. So f prime or f dash, this denotes the derivative, and this with a square bracket we write it like at x is equal to x naught. So this is a mathematical definition. And one more thing to note down, this h which we introduced, it can be both positive and negative. Through geometrical definition in that graph, I just showed you h on the positive side. We moved from x naught to x naught plus h. We increased the value of x naught, but you can decrease it too, right? So the h can be positive or negative. So with the h can be both positive or negative, we can have two derivatives, left hand derivative and the right hand derivative. So that means if you are at a particular point, if you are at a particular point x naught and you increase the value of x naught to some point and then you see the variation, that means you are trying to compute the right hand derivative. So h is becoming to 0, h is becoming closer and closer to 0 from the positive side. But if you reduce if you take h negative, that means you go from x naught to x naught plus h, but h is negative, that means actually you are subtracting something from x naught. That means you are computing the left-hand derivative. So what we are trying to do, we are trying to look at the variation in the value of the function from both the sides when you approach x naught either from its left or from its right. So both left-hand derivative and right-hand derivative should exist and should be equal for the derivative to exist. So now I will show you how to compute derivative of a particular function. So I have chosen a very simple example, fx is equal to x square. So as for the definition, the derivative at a particular point, x is equal to x naught, is given by limit h tending to 0, fx naught plus h minus fx naught by h. So fx naught is x naught square and fx naught plus h is x naught plus h whole square. So if you substituted both of these into the definition, you will get this one. And just by this simple calculation, as you can see, I got this one. And this h and h gets cancelled. And once you use limit h tending to 0, the final answer is 2x naught. And all of us knows this, the derivative of x square is 2x. So we already know this, but because that is something has been already computed using a standard list of formulas. So you might have seen that the derivative of the function. So if my fx is x raised to power n, the f dash x is given by nx n minus 1. But remember how this is coming. This is actually coming from the first principles definition. So all of the formulas which you see for the derivative are nothing but the consequence of the fundamental definition. So that's all for this video lecture, and I hope you had understanding the derivative. Thank you.